So, last few videos I've been making reference that the math might get a little bit harder. And so in this video, we're going to go over some of the algebra techniques you need to refamiliarize yourself with. It's nothing you haven't seen before, and again, the ICE table process doesn't amend itself at all. Like, you go through the same process we've been practicing. It's just I'm going to remind you that at some point when you solve for an x, if we have a quadratic equation, we might need to use a quadratic formula. Okay, so we see that this problem, we're given a KC, we're given some initial information. What's the concentration of all species at equilibrium? Again, we're given a K, we're given a reaction, we organize our thoughts, all right, with an ICE table. So I'm going to put 1.00 times 10 to the minus 3, initial concentration of H2. Initial concentration of I2 is 2.00 times 10 to the minus 3. No initial information given about HI. That becomes a 0. None of these are solids or liquids, so they all matter. We do a Q versus K check using our I information. We see that Q equals 0. Q is less than K. So again, we note down that with our Q versus K check, using our I information, we have a shift in the reaction to the product side. To get the equilibrium, we don't have enough products, so we need to make more. Plus 2x, I plus c equals e, 2x, minus x, all right? 1.00 times 10 to the minus 3 minus x, and 2.00 times 10 to the minus 3 minus x. We now have E information. What's the concentration of all species at equilibrium? Separately, what's this concentration? What's this concentration? And what's this concentration? Well, to figure out what that is, we need X. So let's set up, just like we did before, using our E information. What the math for this looks like. Well, there is my KC, right? So I know I get to take, right, my product information. Remember, there's a stoichiometric coefficient of 2 associated with this. So I'm going to square it, right, over my reactant information, each raised to the first power. 1.00 times 10 to the minus 3 minus x times 2.00 times 10 to the minus 3 minus x. So again, we're at a situation, right, where we need to solve for x. And this leads algebraically to something that's a little bit more difficult to solve, all right? So let's kind of take this step by step for this first example, all right? And let's make sure that we can at least together get to the point where we need to invoke the quadratic formula. We're going to use the FOIL method on the bottom here, all right? And we're going to square that term on the top. So we're going to get 49.5 is equal to 4x squared over a quadratic in itself. This times this is going to give me 2.00 times 10 to the minus 6, right? This times this plus this times this is going to give me minus 3.00 times 10 to the minus 3x. This times this gives me plus x squared. We use that FOIL method on the bottom, right? And again, if that's something you need to remind yourself algebraically of how to do, well, we just kind of did it together there. So go back over that and make sure you can reproduce it in your notes yourself, okay? Now, algebraically, we need to build a quadratic. This isn't like other examples we've seen before. There's an x squared here, there's an x squared there. It's not just a simple x to solve for. So the next step is to take this and bring it to this side over here. And so I'm just going to rearrange this a bit. I'm going to bring the 4x squared to this side just for my own personal sake in terms of writing this. And I'm going to take 49.5 and multiply it by all of this, and then that's going to be on this side that I'm moving to this side of the equation. All right. So if we do that math, 49.5 times this gives me 9.90 times 10 to the minus 5. 49.5 times this gives me minus 0.1485 with three significant figures times x. And I'm going to get a plus 49.5 x squared. So just to reiterate what I did, I just kind of flipped this equation. I wrote this on this side and this on this side. And then this denominator has to multiply to the 49.5. That's going to be on the opposite side of the equation as the 4x squared, right? So algebraically, you should be able to come up with that. We're close to writing this like a quadratic. Remember, when we solve a quadratic, we need to gather everything onto one side of the equation, and the other side of the equation is going to be equal to 0. So we're going to subtract 4x squared from both sides, and I'm going to rearrange this and write it like we normally would, a quadratic equation. So I'm going to have 45.5 x squared, after I do that subtraction, minus 0.1485 x plus 9.90 times 10 to the minus 5. Now we have this form where we have, a quadratic, different powers of x, all sort of organized on one side of the equation. On the other side of the equation, we have 0. And now we can use the quadratic formula. So you kind of not often, but you do end up with these semi-often enough that you have to be super comfortable with how to solve quadratically for an x. So remember how you do this. Our quadratic formula says, there's two x's that we get, and they look like minus b plus or minus the square root of b squared minus 4ac. All of that is going to be over 2a. The reason that there's two x's is you do this first with the plus, and then you do it second with the minus. So what are a, b, and c? Well, the reason that we organize ourselves in this manner down here, whatever is in front of the x squared is a. Whatever is in front of the x is b, including the negative, and if there was a negative there, you would include it as well, but just don't lose that. And then whatever is left over that doesn't have an x attached is the c. So this is how you would set it up. I want you to practice using this quadratic formula. What you get for the x's, and there's two different x's that you get, as we would expect, is we get 2.3298 times 10 to the minus 3. All right, and then we also get an x, or x that's equal to 9.3389 times 10 to the minus 4. So do the quadratic formula and see that those are the two x's that you get. Now for our ice table problem, only one of these x's will be valid. Remember that our ice table has concentrations inside it. If you get a negative x here, a negative concentration doesn't make sense, so you get rid of it and you use your positive x. I just want to remind you what our E slot looks like on our ice table. I'm going to write it down here, all right? Underneath the H2, we had 1.00 times 10 to the minus third minus x. Underneath the I2, in our E spot in our ice table, we had 2.00 times 10 to the minus 3 minus x. And then over here with our 2HI, we had a 2x. So you have to pick one of these x's to make sense. And I just said an important thing. If any of these x's are negative, well, you would put that x in the ice table and it doesn't make sense to have a negative concentration. That same thought process applies, excuse me, when you look at these E settings here. If I take this x and I plug it in here, and you can even do it in your calculator, what you're going to get with this x is a negative concentration for H2 at equilibrium. And that doesn't make sense at all, okay? The lowest concentration you get for H2 is it all goes away. So this x right here, there's no way that it can be valid. Even if you plug it in here, right, what are you going to get? You're going to get something that's negative. So this x is no good. So you always kind of do that determination. You see what x makes sense for your ice table in terms of what it's going to do to your E slot. So this right here, this must be our actual x. So of the two x's that you get from the quadratic formula, one will make sense. The other one will produce a negative concentration and it won't make sense. So now let's answer the question. The question was, what's this concentration at equilibrium? What's this concentration at equilibrium? And what's this concentration at equilibrium? Paying attention to significant figures. All right. What we get for H2 EQ, right, is we get 7 times 10 to the minus 5 molar, and now I'm reporting it with molarity. I rounded the correct number of significant figures. Make sure that you can do that math yourself and see why there's just one that's given in the end. All right. For I2 EQ, I'm going to take my x, subtract 2.00 minus 3 minus x. Okay, so I'm going to plug that in my calculator, and what I get is 1.06 times 10 to the minus 3 molar. And then 2 times this x is what I get for HI. So my HI at equilibrium is going to be 1.9 times 10 to the minus 3 molar. So make sure you can reproduce all this mathematics, get comfortable with use of the quadratic formula. Let's set up one more example together for quadratic formula practice. And again, if you have to go back in your algebra notes and you have to look up, examples of quadratic formula or do a Google search and do quadratic formula practice, like I said, it does show up fairly regularly in these types of problems. So let's take a look at this example real quick. So PCl5, which is a gas, is in equilibrium with PCl3, which is a gas, and Cl2, which is a gas. Let's say that I give you a Kc that's equal to 0.800, and you read the problem and you figure out that you're given an initial concentration of 1 molar for this, an initial concentration of 1 molar for this, and an initial concentration of 1 molar for this. And that's all you're given for the problem. And what you want to figure out is what the equilibrium concentration of each species is. Well, from here, what's the next step? So take a second, think about it yourself. Right here, we need to figure out what the rest of the ice table looks like. And the way that we do that, the next step is, right, K versus Q. So we take our I information and we calculate a Q. Well, this looks like 1.00 times 1.00, both raised to the first power, divided by 1.00. Well, that's pretty easy. We get 1.00. How does Q compare to K? Well, in this instance, we can see Q is greater than K. Do you remember what happens now? Well, Q is too big, which means that the products are too big. And so then that tells us that we're moving in this direction, okay? So to get to equilibrium, we have to lower the products and add to the reactants. So then let's finish out this ice table now that our K versus Q check is complete. And so we're moving in this direction, so I'm going to put a plus X here. We're leaving this side, so I'm going to put a minus X here. Just do a check. All pluses on one side of the dash, all negatives on the other side of the dash. Okay, good, I didn't mess up a sign there. I plus C equals E. 1.00 plus X. 1.00 minus X. 1.00 minus X. And we see why that K versus Q is critical in terms of setting things up correctly. Our K is equal to product concentration at equilibrium. Remember, E info comes down to K, 1.00 minus X, times 1.00 minus X. We could write that as a square, but I'm just showing you where everything is coming from directly. 1.00 plus X. Now we see that we're going to get a quadratic, because what are we going to have to do in the top? We're going to have to FOIL it, right? And then we're going to get an answer based off of solving the quadratic formula. So I wanted to do this setup and I wanted to turn you loose on the math. All right. So what I get from the quadratic formula, and you're going to fill in the gaps yourself, is I get two different x's. All right. So I get an x that looks like 2.72665, and I get another x that's equal to 0.07335. So that would be good math practice to get to these numbers, but then we also have to interpret these numbers. And so if these are the two x's that you get from that mathematical process, which one will not make sense? Right? Let's put this here and put this here. And what do we get? 1 minus something that's bigger is going to give us a negative concentration. And so we know that that's not going to be the correct x to use. And so this x is the x that we use in each one of these spots to get the final answer. Okay? I think when I did this, I got one significant figure there, but you can check your work. But we'll see now that when I use the correct x in the correct spot, what we're going to get here for the equilibrium concentration is 1.07 molar. And what we're going to get here is 0.93 molar and 0.93 molar. Again, we skipped over some of the math in terms of the quadratic formula, but I wanted you to see one more setup and one more practice problem where you do have to use the quadratic formula to solve for an x.